Okay. Hello, everybody. All right. Okay, we're on. Let me just mute myself. Okay. Thank you for joining us today. For SUHO's webinar series. We're very excited to be bringing this to you throughout the month of April, whilst we're all in our homes and doing our best to keep going on. So the first webinar that we're going to be presenting to you is about air tightness testing. So welcome to the introduction to air tightness testing. What we're going to cover today is basically what is a blower door test, what is the testing, what happens during a test, what are the benefits of an air tightness test, a little bit about bushfire resilience, something about the changes that are coming to the National Construction Code on May the 1st, and a little bit about Green Star as well. So what is blower door testing? Blower door testing is basically a way of quantifying the air leakage within a building. So air leakage is defined as the uncontrolled movement of air through the unintentional cracks and gaps in the roof, walls, and floor of a building. So it's important not to get that confused with ventilation. Ventilation can either be passive using your doors and your windows, or it can be mechanical using a mechanical ventilation system. That is not what we're talking about when we talk about air leakage. We're talking about the air that's moving in and out of the building fabric that should not be moving in and out of the building fabric through the gaps and cracks that are left there basically by the people who build the house. So this ventilation is very important, but it has to be on purpose. And the Your Home website states that up to 25% of winter heat loss is actually via the gaps and cracks in your home that shouldn't be there. So blower door testing is a way to quantify that air leakage and fix it. So what happens during a test? Typically, somebody will come to your building site or to your home or your office location with some equipment. That equipment varies. How much equipment we bring varies depending on the project. But essentially, we load some fans into a temporary door frame, which is installed in one of your external door frames, and one of the external doors in the building. The number of fans we use are determined by how large the building is and how leaky it is. And this fan exerts negative or positive pressure onto the building envelope. The building is pressurized to a pressure differential of 50 pascals. So what that means is inside the building is either 50 pascals below or above the outdoor pressure. And that's all read using hoses and using gauges. The readings are taken on the gauge, and that air pressure differential, all of the air pressure readings are recorded on a gauge, which then is fed through to a laptop. And these graphs that you can see are the data being recorded. So the top graph is from a multi-fan test where all of those red squiggly lines indicate one separate fan. The green line is the building envelope pressure. The bottom graph is a single fan test where only readings from only one fan are being recorded. Finding the leaks is quite simple. When the house is under negative pressure, the air from outside is actually sucked into the building through all the gaps and cracks that shouldn't be there. So you can see this image on the left, which is also from the Your Home website. These are the typical places in a home or even in a commercial building where air gets in. So anywhere that the building fabric is penetrated, so downlight penetrations, exhaust fan penetrations, windows, taps, electrical, air conditioners, chimneys are a huge one, particularly in older buildings where they're generally open fireplaces. Huge areas of air leakage. Timber floors are another really big one. And exhaust fans are a big one because sometimes they don't actually have dampers on them. So I've got a little video here which will show you another place that air typically leaks that we often don't think of. Electrical power points. So you can see we've got a smoke pen that we're using to show the air leakage. And this footage was taken in quite an airtight structure. So all the leaks that we found were quite small, but the PowerPoints was probably one of the biggest leaks in this particular building, which was quite interesting. But we find that air leaks through PowerPoints typically in most homes. You can also go around with your hand and simply feel where the air leaks are coming through. They're usually big enough to feel by touch around door frames, window frames, underneath exhaust fans, underneath downlights, anywhere there's a penetration underneath your sink where your plumbing penetrates through. And the image on the right is actually a thermal image of an exhaust fan that is not sealed and the house is under negative pressure. So the purple marks that you can see is air leakage. So under a thermal camera, air leakage looks like paint is splashing on the surfaces around it. So thermal imaging is another very useful way that we find air leakage. It's most useful in the colder months because the indoor and outdoor air temperatures need to be at least 5 to 10 degrees different for the imaging to show up in a useful way. So during the summer, we tend to use feel or smoke to find the leaks. In winter, the thermal images are much more interesting. So the top image is an air conditioning duct. The image on the top right is a window architrave that is leaking quite significantly. All of the windows in this house were leaking at that same level, which was shocking for the owners. Made sense that their house was so cold after they saw that. The image on the bottom left is where an insulation batt has been taken away from the ceiling in order to fit a downlight. So thermal imaging is really useful for identifying missing insulation as well as air leakage, and this is quite a common issue that we find. The image on the bottom right is a steel frame, and as you can see, the frame really lights up, which indicates thermal bridging issues, but that is a discussion for another day. The red pen test, you might have heard of this before. It's something that anyone who knows about air tightness will talk about. The red pen test is the easiest and cheapest and quickest way you can make sure that your air barrier is identified at the beginning of a project. So before any ground has been broken, this red line should be drawn on your plan set so that anyone who looks at the plans, all of the trades, understand that 1, there is an air tightness strategy in place, and 2, exactly where they need to pay attention. So in the example of the residential home, you can see that the air barrier goes all the way around the perimeter of the home, but excludes the garage. And the reason for that is the garage is an unconditioned space, and you want to be controlling the air within the conditioned space and excluding it from the garage where there's going to be things like paints, fumes from your car, chemicals, etc., etc. The same applies to a commercial building where the red pen test is drawn around each level. It often is drawn around things like areas such as plant rooms, which are excluded from the building envelope. But basically, it's the cheapest and easiest way to identify the air barrier, and it generally follows the line of the insulation. This image here with the green boxes, that's just to identify to you some areas that we use to work out the air leakage results. So the dark green is the envelope area in square meterage, and the green is the volume of the building, and I'll go into that a bit later. So there's a few different types of tests that you can do on any type of building. You can either test a small portion of the building or you can test the whole building. The whole building is really the best way to test a building for air tightness. If you test a small portion of the building, you can get some really good results and identify some really important air leakage pathways. But the number that you get at the end of the test doesn't make sense because you're not testing the entire external envelope. You're testing internal areas as well. And at the end of the day, when it comes to air tightness, we don't really think about what leaks between floors or between rooms. That's not going to impact your energy efficiency very much at all. What we are focusing on is what is leaking out of the external envelope. So if you're testing internal areas, then the numbers that you're getting are quantifying internal leakage, if that makes sense. Now, the plan is to actually create a separate webinar just on this topic, so I won't go into it too much today, but if you're interested in learning about the different types of tests and why it matters, then stay tuned. The benefits of improved air tightness are many. Of course, reduced energy costs because you are not heating and cooling your internal air and have it leak out the gaps and cracks that shouldn't be there within half an hour of you turning off your cooling. I'm sure many of you have had that experience where you are feeling a bit cold, so you flick on your heater and you think, after about half an hour or an hour, you think, yep, I feel okay now, and you turn it off and you're cold again within 20 minutes or something like that. That's largely due to that nice warm air that you're paying for going straight out the gaps and cracks, amongst other things, but that is one significant contributing factor. So if you have a more airtight building envelope, you're obviously going to be more comfortable because the air inside your building is more controlled. So the idea of an airtight structure is actually to control your indoor environment. You have healthier indoor air quality because you're stopping all of the allergens and chemicals and pollution and whatnot coming inside your building from outside. There is a flip to that where you could actually be trapping unhealthy air inside your home, and that is a very important point because you cannot create an airtight structure without also thinking about a ventilation strategy. The mantra in this industry is build tight, ventilate right, and that's very, very important to remember because if you build a really airtight structure and don't think about your ventilation strategy, you've got you can create knock-on effects with indoor air quality, with indoor air humidity and moisture control. There is reduced small particle infiltration, again, like I mentioned earlier, reduced moisture infiltration because once air enters your building structure, it brings with it moisture. If you have a mechanical heat recovery ventilation system, you must have an airtight structure, otherwise it doesn't perform very efficiently. So that's another benefit. If you are going to have a mechanical ventilation system, your envelope must be airtight. And you get less unwanted visitors, spiders, cockroaches, mice. They're in my house, and the only way they get in is through holes in your fabric that shouldn't be there. I mean, we can leave the doors open and they come in, but I would hazard a guess that mostly that's not the way that spiders and cockroaches get into our house. So, yeah. An airtight structure is also more resilient to bushfires, not because they don't burn down, but because they're less, they're not going to be affected as much by embers, and by smoke. So this on the left-hand side, this is a Facebook status that was posted by a friend of mine that I went to high school with. She lives in Canberra. And during the bushfires earlier this year, she posted this and said, after a brief respite, the smoke is on its way back. Time to tape the doors and windows again. And I thought, well, that was a fair indication of the standard of build quality because they can shut their doors and windows, but it doesn't stop the smoke coming in through the gaps and cracks. And she had an 8-month-old baby and she was very concerned about this. So they were actually going around and taping up the gaps around their doors and windows. On the right-hand side, there was another article by a gentleman in the Canberra Times, and a gentleman named Jonathan Milford said that his windows didn't shut properly and that it was a little bit less smoky inside than out, but not too much less smoky. So this is a couple of anecdotal stories quite close together during the fires, and I'm sure this story was repeated across the whole bushfire zone during that terrible time earlier in the year. The other way that bushfires that homes are made more bushfire resilient by making them airtight is because a major way that houses actually burn down, one of the major reasons house fires start during a bushfire season is because ember attack. Embers can travel up to, I think I read, 40 meters or more. And if an ember lands in your windowsill, gets under your windowsill somehow and starts to smolder, and then your curtains catch on fire. That's a very significant risk during bushfire. So if you've got an airtight structure, then you're not going to get embers inside your window frames. So as I was saying earlier, embers get in gutters, underneath doorways, gaps and cracks around window frames, gaps in roof spaces and underneath the floor. So the same applies to all of these different areas where embers can sit and smolder and catch a light. It is my hope that AS 3959, which is the bushfire, constructing in a bushfire zone Australian standard, it is my hope that they will address air tightness as part of maybe a revision of their standard post-2020 fire season. An airtight building that is correctly ventilated is one very good way to improve the resilience of a dwelling during bushfire and protect the health of the occupants. So you're protecting from ember attack as much as you possibly can, as well as obviously clearing gutters, clearing leaf litter and all that sort of thing, and protecting health of the occupants by stopping smoke getting into the house. This graph on the right is from a CSIRO study that was done in 2015, which is now 5 years old, which doesn't seem like that long ago, but it is. That stated that they did a lot of research across the country, doing some blower door testing. They tested about 130 houses across all of the capital cities in Australia and put it together in this report. The outcome of that report was that the average air changes per hour across the country, which is one measure of air tightness, the amount of time it takes for all of the air inside a home to be completely replaced at a pressure difference of 50 pascals. So when you hear the term air changes per hour, that's what it's referring to. And this study said that the average across Australia was 15.4 air changes per hour. To put that in some context for you, Passive House, which is the gold standard of residential building internationally, has to achieve 0.6 air changes per hour. So that's obviously the other end of the scale. That requires a very deliberate design and execution strategy. And to give you some further context, the Building Code of Australia, which I'll talk about again in a second, is mandating a score of approximately 10. So across Australia, the average home is not achieving what it needs to be compliant with the building code. And as you can see, there are some outliers here. South Australia is not doing too bad. On the ground across the board, we did okay. So that's positive. But these homes, it's probably interesting to note as well, were no more than 4 years old. So these weren't leaky old bungalows that were being blower door tested. These were all new homes. National Construction Code 2019. So this building code, as you are probably all aware, was introduced on the 1st of May last year. We have been given a 12-month grace period, which runs out on the 1st of May this year, which is in 4 weeks, a month from today. It's a very positive sign that that blower door testing or air tightness testing has been introduced into the building code. At the moment, it is still voluntary, so it is not something that you have to do by any means. It is one way, it is a performance solution, and it is one way of verifying building envelope sealing under the new building code. So you can still go down the DTS route if you like, the way builders have been doing forever, or you can get a blower door test done. And that goes for commercial and residential. The commercial code, as you can see, has different requirements for different building classes in different climate zones. So you can have a little read of that I'm not going to go through it now. It's too many numbers to quote. But in residential blower door testing across the board, you have to get a score of 10. So brief little note here about the way air tightness is measured. There are two different ways of quantifying air tightness. One is air changes per hour, which I mentioned earlier with this study here. The other is permeability, and the building code talks about permeability rather than air changes per hour. Permeability is used probably internationally. There's only a couple of places, Passive House is one of them, that use air changes instead of permeability. I'll go back to this little image here with the green boxes. Whoops. This one here. So permeability is worked out based on the building envelope, which is the dark green on this image here. Air changes per hour is worked out based on the building volume. So if you apply that to a residential setting, the results are more or less the same. If you calculate square meterage of the walls, roof and floor of a house, it will be more or less the same as the volume. When you get to commercial sized buildings, the volume is significantly different to the building envelope area. So the two results are going to be quite different. I'll go back here. The results are worked out. So the amount of air that it requires to create a pressure difference of 50 pascals is divided by either the building envelope area or the volume, and that's how you get your result. So I guess the moral of this story is the building code is using cubic meters per hour per square meter, which is referred to as the permeability of the building envelope. And a score of 10 is reasonable. It is not particularly stringent. It's not too difficult to achieve. And I'm personally just very pleased that the building code has included blower door testing, because it means that more people are going to be aware of it and talking about it and getting used to this terminology. So that's really positive. The Green Building Council of Australia. This is one of the only organisations that does mandate blower door testing in Australia. Under their credit 2.2, they have air permeability performance testing, which is another term for blower door testing or air tightness testing. They have different cutoffs, different targets for different types of buildings. The most common building that I have tested has been an office. So in order to get one green star point under point 2.2, you have to achieve a permeability of 20. So I referred before to a permeability of 10 being not particularly hard to achieve in a residential setting. 20 is quite leaky. So in order to get one green star point, it's not super difficult. In order to get the innovation points that are associated with normal or best practice, that is a little bit more difficult, and you would have to get some advice more than likely to achieve normal practice. And definitely to achieve best practice air tightness if you were going for those innovation points. So you'll get 1 point for achieving a score of 20, a permeability of 20, 2 points for achieving a permeability of above 7, and 3 points for achieving a permeability above 3 in an office or in a naturally ventilated office, just in this example. A suitably qualified practitioner, the guidelines state that a suitably qualified practitioner has to be the one to carry out the test. And if you are looking for one, if anyone out there has a Green Star project and you're looking to have a test done, the ATMA website lists everyone in Australia who is qualified to do that test. So you can, if the link is on this presentation, I can send you this presentation if you like after we're done here. Or I can send you the link to the ATMA website as well. ATMA stands for the Air Tightness Testing and Measurement Association, and they're actually based in the UK. We now have an Australian version of ATMA, which is very exciting. But they have been a huge help with getting the industry moving here in Australia. Going back to some of those comparisons I was talking about before. So Australia-wide, CSIRO study said that the average score in Australia is 15.4. I'm going to refer to it as a score because flicking between air changes and permeability gets confusing. So we'll just pretend that they're approximately equal. 15.4. In the UK, they have to get a score of 10 in order to get their occupancy. So over there, they have a couple of different tests done on all of their houses, or most of their houses, and they have to have a test done to get occupancy, a compliant test. And having a funny discussion with one of the ATMA representatives, he said that sometimes it can be the case where the truck is in the driveway, moving truck, waiting for it to move a family into a home, and the blower door test will fail and the family can't move in. So that's pretty extreme, but that's the way it is over there. Passive house must achieve a score of 0.6. The Department of Defence are another example of an organisation that require air tightness testing, and they use very similar guidelines to the Green Building Council of Australia. And as mentioned earlier, the cut-offs there for an office are as we just discussed. So there's a few different places, a few different organisations that require air tightness testing. It is not required in general residential and commercial construction at this point in time. It is an option that you can use under the building code to verify your building ceiling. And I do encourage you all to actually think about it, because the reason is that you can't, air tightness puts a number on something that is invisible. And I guess the risk as air tightness and energy efficiency requirements continue to increase over the coming years is that you will accidentally build a structure that's too airtight and you won't know. You won't be aware of what you've actually accidentally done. And then the occupants in that building could be subject to poor indoor air quality. They could have problems with moisture buildup and mold in their home. So the build tight, ventilate right mantra is extremely important. And I mean, I, for one, just like knowing the data side of it is very interesting to me. So if you're the same, if you want to know, if you're a builder and you want to know where your current building stock is at, it's a really useful thing to just get a blower door test done and just kind of benchmark yourself. We've had a few builders do that and they find it very valuable. The first time I saw a house under negative pressure and used my thermal camera, I was fascinated at all the leaks that we found that I had no idea existed before. So it is a really valuable exercise. So that's all I have today on air tightness testing. I would like to say thank you very much all for your time. I hope you learned something today. If you have any questions, you can contact me by just going to our website. All of our contact details are there. And there we go. And we have a couple more webinars coming up tomorrow and Friday. So stay tuned if you have any need to know about the residential code changes or the commercial code changes. They are significant. So if you're not aware of what is coming up for you on May 1st, then stay tuned for the webinars on Thursday and Friday. Alrighty. Well, thank you all very much. And bye for now. Or should I wait for questions? Maybe I'll wait for questions. I'll just pop this back up. I'll just sit here until I'm cut off. What have we got? Let's see if there's any questions. I wasn't keeping an eye on the chat while I was doing this, so what have we got? I hope everyone's doing well out there and keeping safe and healthy and sane, working from home as we are. Jared Oakley, what were the differences in commercial settings, volume versus envelope, that were the same outcome in residential? What were the differences in commercial settings that were the same outcome? I'm sorry, Jared, I don't quite understand your question. Deepanjali, you are welcome. Shiva, I'm glad you found it informative. Ben, you are welcome. What are the differences in commercial settings that were the same outcome in residential? You can't really compare. I'll just try and say a few things. You can't really compare commercial and residential testing. It's the same, but it's different. And the reason that we use permeability in across the board testing commercial and residential buildings is because they are comparable numbers. Because the volumes are so vastly different in residential compared to commercial, you could get a false outcome using the volume of a building because it is so large. So what we're really trying to test is the building envelope. We're testing what leaks out of the building envelope. So that is why we use the area of the building envelope to quantify and normalize the airflow to get a result. So I don't know if that answers your question. You mentioned the calculations were different. The calculations aren't different. It's just that we use, we measure, I actually do both. Like for when I'm testing a home, I will usually work out, it's quite easy when I'm doing the calculations to work out both. So I'll work out the volume of the building and I'll also work out the building, the square meterage of the building envelope. And I will present the client with both results. The one that it depends on what standard they're trying to comply with. If they're trying to comply with passive house, then I give them the air changes. If they're trying to comply with the ATMA standard that we saw under the Green Star specification, or if it's a defense project, then we use permeability. So it really depends on what kind of job it is and what they're trying to comply with. But under a residential setting, I usually give the client both so they can see what the air changes result is and what the permeability result is, because it's just interesting. And air changes is easier to think about in your head. It's an easier concept to understand. How often is the air in this room swapping out every hour? It's easier to understand that than how much air is leaking out of every square meter of my house. Like, it's a little bit more obscure. Shiva, is NCC 2019 the first code volume to introduce air tightness testing? Yes, it is. It's very exciting. Oh, good. Thanks, Jared. I'm glad that made sense. It's the first Australian building code, Shiva. Obviously, I presume you meant Australian. Yes, it's the first Australian building code to introduce air tightness testing. And I'm really looking forward to all the new conversations I'm going to have with so many different people who start to become aware of this service. There haven't been any more questions for a while, so I guess I'm going to assume that that's everything. So thanks again. Jared, the red pen test, right? Like, awesome. Once you know about it, it's so obvious. Will wells and other rating tools indicate air tightness testing in upcoming years? Shiva, I don't actually have any experience with wells. Well, I have a little tiny bit of experience with wells, but that is a question I can't answer for you at the moment. If you would like to send through your email address, I can certainly find out for you. And the thing is, I mean, air tightness testing is becoming it eventually will become a code requirement. There will be some sort of compulsory testing down the line. I don't know when that will be. But for now, it's just a really, I mean, it's in the code and we can use it to comply with the code, but it's also just a really useful tool, a really useful way to understand more about the buildings that we are building and a way to compare buildings that we are building. It's a post-construction audit, and at the minute there aren't any post-construction audits in Australia. So if you tell your building team that you're having an air tightness test done, they know that their building work is going to be checked and they will cut less corners. We might finish up there, I think. Thanks, Julia. Thanks, everyone, for all your comments and questions. This was fun. Great, Shiva. Hope to see you again. Bye, everybody. Take care.